Today, we're diving into an idea so powerful it basically saved physics from itself, Niels Bohr's model of the atom. Seriously, it's a story about how one brilliant insight explained why the universe doesn't just poof, collapse in on itself. Let's get into it.
So back in 1913, this simple-looking drawing of an atom cracked a puzzle that the smartest people on the planet totally stumped. It explained why matter is stable, and in doing that, it built a bridge from the old, comfortable world of classical physics to the bizarre new reality of quantum mechanics. So, what was this giant, universe-threatening problem that this little drawing managed to solve?
Well, to get it, you have to know that before Bohr, the go-to model for the atom was like a tiny solar system. You had the nucleus in the middle, like the sun, and electrons orbiting around it like planets. It's a neat picture, right? But it had a huge, fatal flaw.
Yeah, according to the physics everyone knew and trusted, any charged particle that's accelerating and orbiting as a form of acceleration should be giving off energy, like a tiny little light bulb. That means the electron would lose energy, slow down, and spiral right into the nucleus in like a trillionth of a second. If that was true, every atom in the universe would have collapsed the instant it formed. The fact that you and I are here meant the theory was dead wrong. It was a massive paradox.
And then, onto the scene comes our hero, the Danish physicist Niels Bohr. He came up with a radical fix by grabbing an idea from Max Planck, the idea that energy isn't a continuous flow, but that it comes in these tiny, discrete little packets called quanta.
This slide is the perfect way to picture Bohr's game-changing idea. You see, classical physics saw energy like a smooth ramp. A ball could rest at any height along that ramp. But Bohr's quantum view was totally different. He said energy levels are like a set of stairs. An electron can't be between steps, it has to be on a step. It can't just gently slide down, it has to literally jump from one specific step to another.
So to make this whole staircase model actually work, Bohr had to write a brand new rulebook for how electrons are allowed to behave inside an atom. These became his famous postulates.
First, he just declared that electrons can only exist in certain special orbits with a fixed radius and energy. He called them stationary states. And rule number 2, as long as an electron is just chilling in one of these special orbits, it doesn't radiate any energy at all. It completely breaks the old rules. And just like that, with one bold move, the stability problem was solved. The atom is locked in place.
But okay, you might be asking, why only those specific orbits? What makes them so special? Well, this is where Bohr's third and most important rule comes in. He said that an electron's angular momentum, which is basically a measure of its motion in a circle, is quantized. It can't just be any old value. It has to be a whole number multiple of a fundamental constant. That little n in the formula is the key. It's the principal quantum number, and it can be 1, 2, 3, and so on. But it can never be something like 2.5. This math rule is what determines which stairs, or orbits, are even allowed to exist.
All right, so if electrons are stuck on these orbital tracks, how do they get around? That was Bohr's final rule. An electron can jump up to a higher energy orbit, but only if it absorbs a photon with the exact amount of energy needed to make that leap. And it can fall down to a lower orbit by spitting out a photon with that exact energy difference. It's an all-or-nothing deal. No partial jumps allowed.
Now here's where it gets really incredible. This wasn't just a nice story. The real power of Bohr's model was that it gave us a mathematical blueprint for the atom. You could actually sit down and calculate its properties.
So using his rules, Bohr worked out this equation for the radius of each allowed orbit. The radius, Rn, is equal to n squared times a constant, called the Bohr radius, which is about 52.9 picometers. The important part here is that n squared. It means the orbits don't grow evenly. The second orbit, where n equals 2, isn't twice as far out as the first one. It's 2 squared, or 4 times farther out. The energy levels get spaced out really fast.
Let's just put some real numbers on that. For that second orbit, where n equals 2, we take 4 times the base Bohr radius. That gives us a radius of 211.6 picometers. Simple, clean, and best of all, predictable.
But even more powerful than finding the radius was calculating the energy of an electron in each of these states. The formula is right here. En equals the negative of a constant, called the Rydberg constant, divided by n squared. So for the lowest level, n equals 1, the energy is minus 2.18 times 10 to the minus 18 joules. But hang on, did you notice something? All the energy values are negative.
So that brings up a really good question. What in the world does it mean for something to have negative energy? That sounds pretty weird, doesn't it?
It actually has a pretty simple meaning. It just means the electron is trapped or bound to the nucleus. Think of it like this. We say a free electron that's infinitely far away from the atom has zero energy. As that electron gets pulled in and falls into an orbit, it has to release energy to become stable. It spits out a photon. Because it lost energy relative to zero, its own energy is now negative. The more negative the energy, the more stable it is, and the more tightly it's bound. That's why the n=1 ground state has the most negative energy. It's the most stable place for the electron to be.
Okay, so the model is slick, the math works, and it explains why atoms don't just implode. But here comes the ultimate test. Can it actually explain what we see in the real world? For Bohr, the key was explaining the unique fingerprints of atoms, their spectral lines.
You see, if you take a tube of a gas, like hydrogen, and run electricity through it, it doesn't just glow with a continuous rainbow of color. It only emits light at very specific, sharp lines of color. These are its spectral lines, and they're like a unique barcode for every element. Bohr realized these lines were the smoking gun. They were the direct, visible proof of electrons jumping between his quantized energy levels. Each bright line is the light from one specific jump. And his model could predict these lines perfectly. You could actually calculate them with a simple three-step process. First, you calculate the energy difference between the starting orbit and the final orbit. Then, you use that energy to figure out the frequency of the light that gets emitted. And from there, you can figure out all its other properties, like its wavelength or wave number.
And this is the beautiful result, the knockout punch. The model's predictions match the observed spectral lines for hydrogen with unbelievable accuracy. For example, that jump from the 5th energy level down to the 2nd one, the model predicted it would release a photon of blue-violet light with a wavelength of 434 nanometers. And when scientists looked, that's exactly what they saw. This was the moment everyone knew Bohr was really onto something huge.
So let's just quickly wrap up the core ideas. Bohr's model really boils down to these three key formulas: the rule for angular momentum, which decides which orbits are allowed, the equation for the radius of those orbits, and the equation for the energy of an electron in each orbit. These three equations were the engine behind the very first successful quantum model of the atom.
Now, for all of its incredible success, Bohr's model wasn't the end of the story, not by a long shot. It was, in many ways, a brilliant but flawed masterpiece. Think of it as a crucial bridge, not the final destination.
The model had some pretty big limitations. First off, it only really worked for hydrogen, or anything else with just one electron. The moment you tried to use it for helium, with 2 electrons, the math just fell apart. It also couldn't explain finer details, like why some spectral lines are actually made of 2 lines very close together. And it had no answers for how atoms behave in magnetic fields, or, maybe most importantly, how they join together to form molecules.
But, and this is a huge but, despite those flaws, the importance of this model is just immense. It successfully introduced the idea that energy is quantized, it solved the stability paradox, and it perfectly predicted the hydrogen spectrum. It was the essential stepping stone that got physics to abandon the old, simple picture of planetary orbits and start moving toward our modern view of the atom, where electrons are strange clouds of probability.
In the end, what Bohr's model really did was force us all to accept that the universe on the tiniest scales plays by a completely different and much stranger set of rules than we're used to. It opened a door to a new reality, and it leaves us with this incredible question: what other fundamental rules of the universe are still out there, just waiting for us to discover them?